Temperature is a measure of the average kinetic energy of your particles in wherever. Okay? And it's kind of a weird system. We just came up with ways to monitor that, being a thermometer. Okay? And we represent that as that numerical value. Because that's now an interpretation on the energy that we experience, that experience is widely held in a variety of different places. So we get a bunch of different unit systems to represent that energy. So you get Fahrenheit, you get Celsius, and then you get Kelvin, our three primary temperature scales. Okay? Fahrenheit is our English or American version of it. Celsius is the most widely used. And then Kelvin shows up primarily just in science, and Kelvin is more of an absolute way to look at that energy. Okay? So because we have three different scales, of course, we would have to be able to interconvert between them. So it might be helpful to know some idea of where they're based. So for Fahrenheit, we have common temperatures being 32 Fahrenheit and 212 Fahrenheit. Okay? So water freezes at 32, boils at 212. One of the common complaints that comes up with Fahrenheit is, why the hell did you pick those numbers? Because really, this is an arbitrary human scale. We can drop it wherever we want. Okay? So why did they pick 32 to be the freezing point for water?
They didn't. They found water froze at 32 after the system was developed.
But why develop the system? So the system is actually based off of water. Are there temperatures colder than the freezing point of water?
Yeah.
Are there temperatures colder than the freezing point of water that we can experience as humans on this planet?
Probably.
Yeah.
Go to Antarctica.
Right? We could go to Antarctica, but if we don't have to go that far, like when it snows, admittedly it doesn't snow very often here, right? But when it snows, we do drop below freezing. Okay? So they invented a temperature scale that would stay positive. Right? So the coldest temperature they experienced, they established that to be 0. Water just happened to be 32 scale units higher. Right? So that's not a bad system to kind of think about. Depending on how you then divide that out, that's how you go all the way out to 212 for your boiling point. Celsius, on the other hand, went through and established water to be 0. Okay? So again, we're picking a 0 point, and it's, why would we pick a 0 point? Why pick a 0 point for water at 0? How often do we drop below that? Not very often. How commonly do we experience water, and particularly solid water? All the time. So picking a 0 point for water isn't a bad idea, okay, as opposed to the 0 point being the lowest we've ever found. Does that make sense? Okay. Those two systems then have different hash marks, if you will, denoting each of the degrees. Okay. How they decided to divide those up just made the most sense for that system. Okay? So we would now have to be able to interconvert between those. It's not a lovely system to interconvert between. We'll look at it in a second. Kelvin came along, and this is ultimately science. So if we dig into, you remember how we talked about heat exchange in lab? Exothermic, endothermic. All of those are transfers of energy. Right? Well, temperature is supposed to monitor that energy. If we propagate deeply enough or explore deeply enough into the physics behind those systems, what we end up finding out is that there's a case where a theoretical case, where everything has no energy. Okay? Well, at that theoretical point, what should our temperature be? Well, if temperature is the measure of the average kinetic energy, it should be 0. And that would be the absolute lowest we could possibly go. Okay? That's where Kelvin comes in. Okay? Why do we want to establish a 0 point? Well, what are the issues with Celsius and Fahrenheit? They can go below 0. Well, why do I care? What happens to the temperature when I go below 0? It becomes negative. What was oxidation and reduction? Just the transfer of an electron, right? Okay. Where when you lost an electron, you became positive. But I just lost something. How did I become positive? because it was a negative thing. The negative sign is kind of the bane of our existence. We created temperature scales in the theory that we would never have to deal with a negative sign. Right? The science one is the one that actually worked well. The other ones, we just hadn't achieved those temperatures to be able to see and visualize those. Okay? Celsius is ultimately probably the weirdest one because it's based off water. And yeah, we can get a hell of a lot colder than water. Fahrenheit at least attempted to do so, but failed miserably. Okay? So Kelvin is ultimately a numerical calculation-based way to monitor the energy. Okay? It directly ties from Celsius. Why? Because Celsius was the most widely used, and so we use that as kind of the framework behind it. What's the relationship? The freezing point for water is 273 Kelvin. You'll notice there's a degree on that. Because Kelvin is an absolute temperature scale, there aren't degrees. Degrees are markers. Because it is absolute, there are no degrees. So we actually have a typo. We can't have those degree symbols in there, which then means I deleted everything else. Whereas Celsius and Kelvin are both degree markers. Okay? Subtle thing, but just point out. So with all of those numbers, we should now theoretically be able to come up with a mathematical system that would allow us to interconvert between those. How many of you want to derive that? Okay. Okay. Celsius to Fahrenheit, or Celsius to Kelvin is easy. Okay. The Fahrenheit to Celsius or Celsius to Fahrenheit is this big, weird, convoluted thing that you may have seen out there. Okay. Dealing with 9/5, 5/9, it's 180 related to something else. Numbers. Okay? Yeah, it's a roaring good time. The big one that you need to deal with is the Celsius to Kelvin, okay? Because Kelvin is an important scale to deal with. To do that, all you have to do is add 273 to your degrees Celsius, and you now get your Kelvin. Okay? For those of you looking very carefully, this says 273, and the equation says 273.15. My response to that, how many of you know the value for pi? 3.14, then some jackhole just went through and said, what? 5, 7, then we got another one, 6. Okay? You've memorized a sequence of numbers. Okay? Why did you bother to memorize that extra sequence of numbers? As you keep repeating out those numbers. Sometimes it's important if you're dealing with sig figs.
Other times, I mean,
How many of you really dealt with sig figs before you got into this class? Yeah, okay. So most of you didn't. So why would it be important if it's not a sig fig issue?
like which sequence is
Why pi? Is that what you're asking?
It adds to the accuracy. Yeah, why did you bother to remember 3.14 and I don't know after that? That's all I got. You use 3.14, 5, 7, 1, whatever, 9, 2. Why did you have to memorize that? 3.14 I'll absolutely give you. But 3.1457, the majority of this class did not memorize that. So no, I'm not accepting that as an important thing to memorize.
Why did we have to memorize 4, 5?
definition?
It's a definition. So,
Because it's different than just
why do you need it? We need it for those extra sig figs. Why are you being told that you have to memorize those sequence of numbers? Because somebody else memorized it. Why did they memorize it? Because somebody else told them. Is it useful for you? When?
You're calculating.
especially with the circle.
Are you asking why pi is important?
I'm not asking why pi is important. What I'm asking at is how many sig figs did you memorize as being important?
3.14.
Most of us did 3.
Okay, why did you stop at 3 and not continue going? Those people, there were some people that did continue.
Because after that, the effect is so little on the overall result.
Okay, why did people bother to memorize that extra information? They felt like it. What happens if you ask someone to recite pi and they can recite out 10 digits of pi? What is your now response to that person?
I don't want your
They're really good at memorizing that detail. They feel better about themselves.
Or they're calculating.
Guess who memorized 273.15? Me. I feel better about myself for whatever stupid reason for memorizing 0.15 as an extra sequence of sig figs.
Does the text go further?
Yes, it goes a lot further. Okay. What are you responsible for memorizing? 273. Okay. It's all about deciding how far you want to go. Since we talked about sig figs and pi, let's address pi and its importance for sig figs. Okay. If you don't carry out the appropriate amount of sig figs for pi, you can't land on Mars. And it's something like 20 digits to land on Mars. If you don't have pi to 20 digits of significant accuracy, you can't land on Mars. It is the difference between missing Mars and flying out into the universe for the rest of your life, okay, and landing successfully on Mars. 20 digits of pi. Sig figs make a really big deal when you deal with larger distances or smaller distances. That's why sig figs become so incredibly important. Okay? So, how do we deal with this? Do you guys need a problem to go through and solve, or you think you can do it? Let's do it? Okay, let's do it. This says body temperature is 98.6 degrees Fahrenheit. What is the temperature in degrees Celsius? Somebody's a nurse. So for those of you looking at this, you might say, well, you just deleted an equation that allowed me to solve that. They're the same thing. Are you responsible for the algebra?
Yes.
Yes. Okay. Do I expect you to memorize either one of them? No. How do you know that?
It's on the front of the test.
It's on the front of the exam. It was already there. Yep. Take a look at exam 1 and exam 2. Your conversion between temperatures is already on the exam. Okay? What's that? You do have to memorize Kelvin because that one's easy and Fahrenheit to Kelvin is a little bit more challenging. So how do we go through and solve this one then? Back to the question at hand. So we'll typically get people going through and saying, well, it's this, and now I go through, subtract 32 from both sides, and I would get degrees Celsius times 9/5. It was 98.6 minus 32. Multiply both sides by 5, right, and do all that math out once you've subbed in those numbers. Yeah?
Yeah.
Okay. There's nothing wrong with that, but is there an easier way to do it?
Yeah.
What's the easier way to do it?
Plug it into the opposite formula that you erased.
You don't have the opposite formula, so is there another easier way to do it?
You can create it out of that.
Create the formula from the system that's already there without substituting in those values. Okay? So degrees Celsius 9/5 equals Fahrenheit minus 32. Right? Degrees Celsius equals Fahrenheit minus 32. 5/9. Now that you have the equation in the format you want, now you should do the substitutions. This is kind of like what we've already done with our conversions. We use the units to establish how to organize where our numbers go. Once everything is in the correct format, then we go through and calculate. Right? The reason being is that if we do individual calculations as we go, we increase the odds of making mistakes. Do the algebra first, then do your substitutions. Make sense? What do you get for a numerical value? 37. Okay, would that be a correct answer?
37 degrees Celsius.
37 degrees Celsius, I'll kind of accept. This is actually opening a can of worms I'm not super comfortable with, but we're going to deal with it anyway.
0.0.
Why are you saying 0.0?
You started with a significant.
It's It's going to come down to your sig figs. How do you manipulate those sig figs through this calculation? Okay. So the suggestion is that we started with 3, so we should end with 3. What kind of mathematical operations did you run? Subtraction and multiplication and division. Okay. Which means our sig figs could largely be controlled by each of those individual calculations. Okay. When you go through and run a conversion, the conversion process should not affect your significant figures. This means that when you do the conversion, you have to make sure each of those conversion factors has an excess of significant digits than you started with. Does that make sense? Mm-hmm. So how many sig figs come through the rest of this? The 5/9 is coming from, and I forget the origin on it, and I should feel bad, but oh well. Okay. It is dealing with the temperature difference between Fahrenheit and Celsius for our water and those differences. Right? And that 32 is coming from that as well. And what happens with these formulas is that we've decided to ignore sig figs. How many of you would like to ignore sig figs at least once in this class? Hear, hear. When it comes to temperature, you will not be tested on sig figs. Okay?
Not be tested?
In this class, you will not be tested on it. Okay? And that's largely because I'm not super confident in the rules behind that, and I don't think it's worth the trouble. Okay? So, 37 degrees Celsius is acceptable. 37.0 is also equally acceptable. Okay? 37 degrees Celsius is not a bad thing to know for body temperature, because if you're now making contact with something, you can transfer that heat into that reaction. You have a rough idea of how hot that container is in degrees Celsius. Okay? It gives you a decent baseline for your general reactions. Kind of makes sense? Okay. So, heat as a concept. Temperature is average kinetic energy. Heat is total energy. Okay? So they're measuring two different things. Temperature average, heat absolute. Because they're measuring different things, would we expect the same unit? No. Okay? The unit for heat is typically joules or calories. Why do we have two different systems? Two different places where these things were monitored and discovered, and those two clans decided that they couldn't agree, so we have to deal with it the rest of our lives. Okay? This is not to be confused with the extra calorie, because there's another calorie that shows up, I believe, with a capital C. Thank you, nutritionists. Also different. Okay? So just be aware we have scientific joules and calories, and then I feel bad kind of calling nutritionists not scientific, but they use a slightly different modified version. Okay? So those are measuring the energy. So let's think about the relationship between our temperature and our heat. We've got two containers here, each of them at 100 degrees Celsius. Do they have the same amount of heat? Okay. Temperature. Do they have the same temperature? Yes. The average energy of those particles are all exactly the same. Right? Do they have the same total energy? No. Why not?
Twice as much water in B.
There's more water in B. Okay? The analogy I typically go to, because it's sort of relevant, is if we had a drop of coffee versus a pot of coffee. Which one are you going to respond to a little bit more shockedly, surprisedly, if it got splashed on you? The pot of coffee or the drop? The pot. They're both at the same temperature. But the pot has a whole lot more drops in it, which means more energy transfers into your skin. You respond differently. Does that make sense? Okay. So that's our difference between heat and temperature. The next thing that could kind of come up is this idea of specific heat. Right? Specific heat is specific to an individual substance. Okay, so all substances respond to heat differently. We already knew this. Right? How did we discuss, or when did we discuss our elements responding to heat differently? When did we discuss our elements responding to heat differently? I would argue 1.2, 1.3. What the hell does that mean? Unit 1, Lecture 2, Lecture 3, somewhere in that range. We talked about how our elements responded to heat differently. Yeah?
Yeah.
Oh,
I wrote
the
about that in
scale
my,
from like the purple to red.
No, that's chemical versus physical changes. What are we referencing when we're saying our elements respond to heat differently? Metals versus nonmetals. Our metals conduct heat, and our nonmetals don't. They insulate. Right? How is that going to change their specific heat? Well, specific heat is the amount of heat energy I have to put in to cause 1 gram of the substance to go up by 1 degree Celsius. So let's think about our metals versus our nonmetals. How much energy would I expect to put into a metal to cause it to go up by 1 degree Celsius? A lot or a little? Metals conduct heat, which means the heat immediately passes through, which means that heat I'm putting in the bottom immediately heats up the entire sample so that it can pass through at the other end. I put in a very small amount of energy, and the temperature goes up by 1 degree Celsius, which means my specific heat for most of my metals will be small. Right? What happens if I move to a nonmetal? The whole point of the nonmetal is that they insulate heat, which means when I put heat at the bottom of it, what happens? Nothing. How much heat do I have to put in to cause it to go up by 1 degree Celsius? A lot of heat. A lot of heat means a larger energy value to cause that degree Celsius change. So we can see a difference across the periodic tables between metals and nonmetals. Typically, our metals have very small specific heats, and our nonmetals have very large specific heats. Right? It's a lot more complex than that, but that at a first pass works really well. Okay? So, how could we turn that into an exam question? A large specific heat means what do I have to do? Lots of energy in to get 1 degree Celsius change. Which means that material is doing what with the heat?
Holding it.
Insulating.
It's insulating it. It's preventing the temperature from going up. What materials are insulators? Did I spell that right, or is that insulter?
You wrote insultator.
Very brutal.
L-A-T-O-R. A-T-O-R. There you go. Insulator.
Right? Insulator?
Yeah.
Are insulators. What materials are insulators? Non-metals. Where are non-metals found? Okay. To the right of our staircase. All right. On our periodic table, what do we find? I also find yttrium, zirconium, molybdenum. What is found on our periodic table? Okay, I'll accept that. Where do you find the word copper on the periodic table? Okay, so let's ask that again. Where do you find the word copper
You do not.
on the periodic table. You do not. What is found on our periodic table? Symbols. What is this question testing?
The symbol and the name.
A bit on specific heat, and because our answer choices are not all symbols, it is also testing you.
On your knowledge.
Do you actually know the names of the elements? On top of which, take a look at most of our answers. They all start with C, to add to that layer of confusion on do you actually know what the element names are. Make sense? All right. So if we go through, we can find calcium where? On the left. So that doesn't match. Chromium. Copper. I don't accept copper yet. First, I would say Cu, left, Pb, carbon, C right. Answer is carbon. Make sense? Right? When you go through and look at an exam question, particularly practice exam questions, what you need to be thinking about is not how is Mike going to ask the exact same question, because I'm not. Okay? What you need to be thinking about is how can Mike quickly and efficiently change the question to still answer or get at the same topic with the minimal amount of work. Minimal amount of work?
You're going to say least,
Why?
because this is the minimal amount of work.
I understand what you're saying. Why do you need to look at the question and say, how would this get changed with a minimal amount of work? Because your instructor does not want to do a lot of work. And for those of you being like, Mike, you lazy, look at the mirror. Okay, we are all inherently lazy, and what we're going to attempt to do is to try and get at that same level of knowledge across the board without drastically changing things. Because what happens if we drastically change a test question? It can confuse you, which means why are you getting it wrong? Because you don't know the content or you don't know the question. So most exam questions have been vetted at multiple levels to ensure that what it's getting at is content knowledge, not can you read. Right? That said, you'll still find questions, right, that are reading-based questions where you have to be able to read it. But most exams, if they've been written well, are vetted at all levels. Okay? Because of that, if I try to change this question too much from the example shown here, I now don't know what I'm assessing when you get the question wrong or right. So what you need to do when you look at an exam question that I said, look, this is a potential exam question, you should absolutely solve it perfectly all the way through. Why? Helps you to process it. Why else should you figure out the answer? Go through and compare exam 1 to exam 2. Practice exam 1 to exam 1. Practice exam 2 to exam 2. You'll find there's a few questions that directly overlap. Why? Because I expect you to go through and review those things. I'm giving you a reward for having done so. So you should absolutely solve everything straight through. Okay? You should also go back and be like, do I actually know the answer or have I just memorized the result? How do I know if I know the answer? Make a small change. So one suggestion was, switch this, instead of being largest, make it least. It's got to be smallest, right?
Sure, smallest.
I think smallest specific heat sounds better than least specific heat.
But now you got
Yeah?
4 metals.
It's heat, is it lowest?
We went from largest.
I mean, we are partnered with the English class, but that's as much as I want to devote to that on this one question. All right? So now we could go through and answer the same question. If it's smallest specific heat, what does that mean?
The most metal.
The most metallic. This becomes problematic because 4 of your answers are metals. So if I change that to smallest specific heat, what else might you expect as a change to the question? The answers should all change.
So only one will be metal.
Mike, so it takes more heat to raise
Yes. Right? So we would expect the answer choices to also change, and let's reference the, laziness here. Chlorine, and let's throw in calcium.
Calcium.
Okay? Make sense? Okay. What else could I do to change?
Just change something else.
Okay? Does that make sense?
Yeah.
So what you're doing with a single practice exam question is writing 3 or 4 others and making sure that you know how to answer those 3 or 4 others. That will ensure that no matter what I throw you, you will be able to get the answer right. Okay? Every test question that you have access to, you have an entire practice exam. That practice exam, you should be able to generate 100 different questions. Yes, sir.
So when you say like non-metals on insulators, would that include bromine or no?
Yes.
Yeah. So that would be actually really interesting.
Okay.
That was the first question.
And so remember, this is broad strokes because specific heat is a lot more involved than just metals and nonmetals. Okay? A lot more involved. Okay? So what we're looking at here is those big sweeping strokes. If somebody happened to know specific heats of those particular materials, it could become very dicey if I'm not very careful with which ones I look up to put in here. Okay? Does that make sense? So I will ensure that the largest specific heat on this list is absolutely neon. Because there are exceptions where things pop around the other direction. And if for whatever freak accident reason somebody happened to know the specific heat or to knew an exception, that's going to now mess with the question, right? Okay? Make sense? Questions? No, because you were bromine. You said smallest.
Wait, you also said to ride the staircase, so would that inevitably include mercury as well, or no?
Where's mercury?
To the left.
Left of the staircase. Mercury is a metal. So its specific heat will be a little on the lower end in comparison to our nonmetals.
So it says it's a liquid.
Irrelevant.
Okay. So
It's still a metal.
okay. So
Yeah.
even if it is, so everything, all right, I got it.
Okay. Uh-oh, come on. We looked at conservation of mass. This is a kind of a fun, tricky one that I'll just throw out there because it stumped tutors. Okay. I've given the equation iron reacts with oxygen to produce rust. And I say it was, I'm making up numbers, 2 grams of oxygen and 10 grams of iron. How much rust was produced?
12 grams.
Okay. And this is where tutors will go, oh my gosh, okay, well, this is Fe plus O2 goes to Fe2O3. And they'll go, oh, it's a mole calculation, which is in this unit. We'll start trying to convert things into moles.
No.
Conservation of mass, you add the numbers up, you get your answer. On top of which, what is the formula for rust?
Not Fe.
It's iron oxide. Which iron? Iron plus 3, iron plus 2, iron plus 4, iron plus 6.
Pick one. Just kidding. 3.
It depends on the form of rust. Rust ultimately just means it's combined with oxygen. So when a tutor goes through and attempts to do this, they have the right intentions, but they're missing a fundamental flaw that they don't know the oxidation state of iron. Okay? So be careful with conservation of mass. It can be used to solve for simple equations where there's only 3 things, typically. Okay? If you've got more than 3 things, you're probably dealing with the mole stuff that you will hopefully see today. Yes, sir.
With the conservation of mass, doesn't like the reactant have to have like an equal number to use
Yep.
all of it?
Yep.
So would there only be like 2 or 4 grams of rust? I'm not sure exactly what it'd be, but it wouldn't be like 12 grams of rust, would it?
So the exact mass out, we'd actually have to run the calculation. Your question makes me think that you think I have the brain capacity to be able to do the mole conversion in my head to be able to determine how much rust there is.
But you're just
No,
asking
no,
for
I
the
can't.
mass. That's all you're
Okay,
asking.
all we want is the mass of that product. Yeah, I definitely don't have the brain capacity to be able to pull that one off. Right? Remember, I'm the one that says 10 to the minus 3 liters is 1 milliliter. Okay, because I would rather let the calculator figure it out. Okay? So, conservation of mass and energy. Einstein comes along and says mass and energy are directly related. That's where we get the famous E equals mc squared, okay, expression. Okay? Or if you trust the Animaniacs, it was actually the Animaniacs that discovered it. They just happened to flip the board upside down after they spelled Acme. It's actually kind of neat.
Yeah.
It was a fun little episode. If you have no idea what I'm talking about, don't worry about it. It's still cool. Okay? Conservation of energy ultimately just says energy and mass are equal to each other through that expression, E equals mc squared. How many of you want to solve that expression? Cool, we don't need to worry about it. You just need to know that they're equal to each other. Do you have to move 151? Then you get to solve that expression. Okay? It's not that big. You just have to solve by plugging in numbers. Okay? It's just not worth the trouble for this class. Conservation of energy. We can convert energy from one form to another, but we can't destroy it. Just like with our balancing chemical equations, we can't destroy mass. Okay? We can't destroy energy. But energy can transition to different systems. And that's a good thing because that's effectively what we've done to be in this room. Right? And to have this lecture. Right? What do we mean? How did we get this lecture?
We converted coal into electric.
We converted coal, okay, into electrical energy. No.
We didn't.
We converted chemical energy in the coal into
Physical
heat energy.
energy.
The heat caused what?
Water to change.
Water to boil. So we now get a phase change, a gas change. That gas rises and it moves a turbine, which is now a mechanical form of energy. That mechanical form of energy we transfer into electrical energy, which we then transport to the room, which then hits our lamps, that then does what? Changes it into light energy, which is now projected out there. Right? That's a lot of individual steps. If we can't convert energy, that process becomes problematic. On top of which, in this room, you're taking notes. To take those notes, what do you kind of need to have? Pen and paper, light. Okay? We're in the middle of a freaking building with no windows. Right? If the lights weren't here, can you see what you're writing? No. How did we get the lights? Same process through that coal plant or solar cells or however, nuclear. Okay? So we don't have to do all of those things. Okay? We could have minimized all of that energy usage. How? Have the class outside. Okay? Which right now may not be a horrible idea. I mean, the weather's nice. But way back at the beginning of fall, that probably wouldn't have been so fun. Right? So we've adjusted to use different forms of energy to make our lives easier or more comfortable. Okay? Those forms of energy usually get categorized out into these 6 things: heat, light, chemical, electrical, mechanical, and nuclear. We just walked through one process. We started with coal, which was chemical. Okay? The chemical turned into heat, which then turned into mechanical, which then turned into electrical, which then turned into light. Each of those jumps, we run the risk of losing energy. Each of those jumps does give us an energy loss. That energy loss is in the form of heat. Okay? When that thing gets too hot, what happens to it? It turns off. Okay? So there is heat being transferred. It's just sometimes not super obvious. Okay? Have you ever felt your car hood after you've driven around a whole bunch? It's hot. Okay? We're losing some of that chemical energy from the combustion of gasoline, and it's not going into motion, it's going into heat. That energy loss explains some of the inefficiencies of the internal combustion engine. Okay? We'll always lose heat. Okay? There's nothing we can do about that. Okay? So it's just kind of neat to think about all of the processes and steps along the way. If we look at mechanical energy, we can look at cannons. Right? Cannon is just mechanical energy, right? You just put the cannonball in there and poof, it just mechanically launches out. It's chemical. Gunpowder in the bottom of that was ignited, causing the cannonball to launch. So all of physics requires chemistry. Remember how we talked about that, right? There it is. Right? The internal combustion engine, depending on how large your car is 4 cannons or 6 cannons. Anybody have 8? Okay, 8 cannons. Okay, 12? Just checking. Okay, all those are mini cannons that we're trying to capture that motion, that mechanical energy to cause a rotation to allow our car to move. Okay, and so we might say, well, all of modern life is this now energy transfer. Well, all of life, period, is this energy transfer. ATP. What is ATP? Adenosine triphosphate. It's biology. Okay. What do biologists tend to do? They just write ATP. Why do they write just ATP? Yeah, don't start that. He said oil rig. Why do they write ATP? What is ATP? Adenosine triphosphate. They're like, oh my God, letters and symbols. I can't draw that. Give me ATP. Dude, ATP is just letters and symbols. Come on. Okay? So we look at the larger structure. What happens to ATP? It turns into ADP. T to D, that's all it is. Simple change, and all of a sudden life exists. What is T versus D?
Losing a phosphate.
Losing a phosphate. We remove that single phosphate group, 3 atoms. I can't count, 4 atoms. 4 atoms. Okay. We lose 4 atoms, and now life has currency to transfer energy. We're looking at the breaking of a single chemical bond. That single chemical bond is enough to drive virtually everything we do as far as existence. That's pretty cool. Okay? Back to chemistry again. It's the energy stored in that bond. Okay? If we can get access to that energy efficiently, we can have even cooler toys. Okay? So, temperature, kinetic energy, physical states. We've got 3 boxes here. What do you think they're trying to represent? Solid, liquid, and gas. Cool. Do all phases have kinetic energy? What is kinetic energy?
Yes.
Kinetic energy is the movement of molecules, or how things move. If you were going to study kinesiology, you're studying the movement typically of the human body. How does the human body move so that you can make it move better or fix it, okay, when it's not moving well? Okay? So kinetic energy, do all of our particles have energy? Yes. Okay? They have varying amounts of energy, okay? And relative to each other, we can make statements, but they will all have some form of movement. Is that movement easily detectable? No. Okay? Because our human eye can't detect that level of energy. What can our human eye detect as far as energy? Visible light. Okay? That's what it's detecting, the form of energy. We don't see the kinetic energy aspect. Okay? We don't have the ability to visualize there. Okay, so all of our phases have kinetic energy. Which one do you think has the least kinetic energy? Solids, because?
don't move as much.
They aren't moving as much. Okay, keep it relatively simple. Make sense? Okay, so let's try one more thing here. Do I have it? Yeah, I do have it. We won't worry about that one. I'm going to say yes, no. Okay. Is it better to fill a gas tank in the cool morning or the warm afternoon? Why is it better to fill it in the cool morning?
You're paying for it by volume and you're getting it more dense.
You're paying by volume, but when we run our reactions to move our car, is it the volume of gasoline that's causing the reaction? No, it's the individual particles, not the volume. So if we could condense the gas down to a solid, we're going to get more per volume than we would if it was a gas. Kind of make sense? So we want cool morning is better to fill gas. This is a common thing that some people have talked about. Oh, you should always fill your car when it's cooler and not when it's hot. Okay? Because that hot, you're paying for nothing. You're paying for air. The amount of money you save through your lifetime on filling it in the cool morning versus a hot, let's go 115 degrees
It'll make you $1 million.
afternoon, right? The money you save there is better spent spending 5 minutes every time you stop your car at a gas station walking around looking for loose change. You will make more money doing that than filling in the cool morning.
What if you do both?
Okay? If you do both, fantastic. For those of you that are like, man, I found $20 walking around the gas station.
Making it rain.
Higher on
Plus all the tanks are
Just-
around anyway.
Just to be aware. Okay? I know, a penny's a penny. It can add up. Okay, so chapters 8 and chapter 9. Okay, couple things I want to address. Number one, dimensional analysis comes back hard right now. Okay, and by comes back, we just left it, right? Okay, so if you don't trust dimensional analysis, you now have to find equations to memorize to do everything in chapters 8 and 9. Okay, the amount of equations that you're trying to find are probably 10, 20, 30 different equations. Okay? If you trust dimensional analysis, there's no process, or there's no memorization of extra equations. But you have to trust and rely on the methodology of dimensional analysis. Okay? That does require practice. If you don't do the practice, you now have no hope of getting the question right. Right? Literally at that point, if you see a question that looks like it involves calculations and you haven't been doing dimensional analysis, bubble in a random answer. Okay? Literally. Stop reading, just bubble it in and move on. Okay? Because that's what you're looking at. Any other time you spend on it is now a bad idea. With the last exam, you could have looked at it and been like, well, I didn't do dimensional analysis, but I know centimeters and meters, I know millimeters and meters, and I can do 3 or 4 conversions to process through that. Okay? Because you knew what centimeters and meters were. You knew what that unit meant. Chapter 8, Chapter 9 are now moving to units that you don't know their meaning. Okay? Arguably, you won't learn their meaning. Okay? But you have to be able to use and manipulate them, because it's that use that allows you to learn that meaning. Okay? That's why you need dimensional analysis. Okay? I will say, when you go out and look at the world, okay, as far as these concepts go, they will push and pedal equations right and left. Why?
What do you mean?
Okay. With density. Did I say you should memorize an equation for density? No, because you just follow the units. Okay? And yet, if you look up density, what do they tell you? Mass over volume. Okay? You don't need that if you have the units behind the system. Okay? And yet, what do they tell you to do is memorize an equation. Why? It is very easy to test, did you memorize a fact than to be able to apply that fact. Okay? If we add that to another level, how happy are you with exam performances being low? None. So if I'm an instructor sick of getting exam performance and am now ranked on my ability to get high exam performance, what am I going to do? Cheat the system by making exams easier, making the content just memorize this formula and use this one formula. You now have a way that you as students go, oh great, I've gotten my A, I'm happy. The teacher goes, well, you got your A, I don't lose my job. Right? I don't believe in that, because you will not have knowledge that you can apply to anything else. Right? That means we will fight through the dimensional analysis process every single day. Okay? Because I want you to be able to apply this to everything else. I don't want you to walk out of the class and be like, well, I'm never going to use that again. Make sense?
In case
Hi.
you missed that, that's Mike's way of saying he cares about you so much he's not going to give you the easy way out. He's going to make you fight with it.
We're giving them more powerful tools.
That's just my turn. I'm just saying.
Yeah. To that end also, the textbook goes through and doesn't address it the way I address it as well. And they go through and say, oh, well, this one's a mass-to-mass conversion, so you need to memorize this equation. This is a mole-to-mass conversion, so memorize this equation. And they start categorizing it so much that what you see is, oh, I need an equation. You don't need an equation. You need the process that they've given you and established. That process will work phenomenally for every single question. Okay? The next thing I want to add is the textbook brings in this concept of volume in Chapter 8 and in Chapter 9. Do not touch that volume with a 10-foot pole. Okay? That is a horrible system that the textbook is talking about. It is ludicrous. It is throughout all common chemistry curriculum, and it is an awful thing to teach. Okay? So avoid the statements using volume in chapters 8 and 9. We'll talk about volume when we deal with 13, I know for sure, and then the other one I can't remember if it's 11 or 12. Okay, maybe it's 10, I don't know. Okay? And all that's going to hinge on is how do we think about and manipulate volume. Okay? Volume really comes into play when we look at gases and liquids. There are two different phases. We'll have two different systems to apply to them. So don't start using what the textbook's referencing, because you'll start using it indiscriminately and indiscriminately wrong. Okay? Kind of, sort of? Okay. So, do we need to do this practice example again? Okay. Okay, we got it, sure. It's not a judgment, it's just trying to establish. What are we attempting to get for an answer? Mass is not a bad idea to identify. Okay, what is that bulk category you're trying to find? Okay, it's in units of micrograms. What were we given? Milligrams. So we could write out our milligrams, 325. As we discussed in the past, that's a bit odd. I mean, that's the only thing you're given, so clearly you need to start with it, but why are we placing it in the numerator versus the denominator? What is 325 milligrams a measure of?
The one item.
It's volume?
No mass.
It's mass. What are we solving for? Mass located where? Numerator or denominator? Numerator, which means I will take my given information and I want to start with that in the numerator. That can help me identify where to place it. Okay? As we talked about with our distance conversions, okay, I would still be a bit shaky with showing in milligrams because milligrams is not micrograms. Why am I choosing to place it where it is? Okay? Is milligrams micrograms? What do we need? We need conversion factors. Okay? What conversion factors do we need? Okay, we could look for a micrograms to milligrams. Does that exist? Okay, not really. So what do I want to convert, micrograms or milligrams? Okay, so what am I going to convert milligrams to? Grams. Is that a conversion factor I'm required to know? Yeah. What is that conversion factor? 10 to the negative 3 is what milli means. The power of 10 will always go with the core unit. The core unit is grams. Okay. What unit would I now have? Grams. Is that what I want? So what do I need? I need to place grams in the denominator so that the grams can cancel. And what do I want in the numerator? Micrograms. Is that a conversion factor I'm required to know? No. Okay. And remember, in a course where we've got tons of content, it's very important to know where those lines are on what you need to memorize and what you don't. Okay? When it comes to the exam, you can always ask, like, did you mean to give this to me? I'm like, oh, crap. Totally right. Here it is. Okay? That's a bit late to be thinking of that. You should have addressed that before the exam started. Okay? That would be something like, if I tell you to memorize it, I did, you should write it down. What did I tell you to memorize when it comes to Greek prefixes? Ouch. It stings a little bit. Kilo, milli, centi. Okay? Kilo, milli, and centi are the three prefixes you need to memorize. You can attach grams to them if you want, kilograms, milligrams, centigrams. It ultimately doesn't matter as long as you realize that gram can be interchanged with any core unit. So it could be kiloseconds. Why would you do that? Because I felt like looking at 1,000 seconds. Okay? It depends on whatever system you're looking at. Okay? So, what is the conversion between grams and micrograms? Oh, that's right. I didn't have you memorize it. So what would you see on the front of the exam? (10 to the negative 6 units is micro units. I'm not writing grams here because it could be liters. Okay? It could be seconds. It could be miles. It can be any unit I want to place in there. In this case, what is the unit? Grams. Where does my 10 to the negative 6 go? No, it does not go in the denominator. It does not go in the numerator. You're like, what? How could it possibly? If it's not in one, it's not in the other. That's because your language is incorrect. It goes with the core unit. The core unit is grams. So where does the 10 to the negative 6 go? With grams. Okay? Language is very, very powerful. If you go through and say 10 to the negative 6 goes in the denominator, the next time you solve this, where are you going to place 10 to the negative 6? In the denominator, regardless of if it was supposed to go in the numerator. Okay? Place the numbers with the units, not their locations. Okay? So that's our process. We had step 1, step 2, 3A, 3B, that's a 3, trust me. Okay? On deciding what those things were. Okay? This format can change and tweak depending on what we're given and what we see when we go through and solve. Okay? And by we, I mean you as an individual, because that's how you get tested. Okay? So when you go through and solve these kind of things, try it different ways to prove to yourself that it does work. Okay? So, you're like, why is that so small? So, we just threw this out there in an old class. Greg already did it to you guys with the nomenclature, provide the process. But he threw this out there, convert 2,437,000 inches into miles. And his rule was you can only use alphabetic symbols. Right?
Oh.
So provide a process to go through and solve that. Right? I really just want you to think about it. What would be some of those steps that you would need to do?
Inches to feet.
Okay? Inches to feet. So I'm hearing that we should be converting inches into feet. Okay? So let's take a look, because we said inches into feet. We had feet into miles. Anybody noticing an issue with how I've got this written already? We didn't actually specify what we wanted for an answer. What did we want for an answer? Miles, and we want that in the numerator. Where did it show up in the little bits of work? Okay? So it's not just what are the conversion factors, but you have to think about their placement of where you place those units. Because if you change the placement of the units, you're going to change the placement of the numbers. So you have to be very specific with how you go through and process. How specific? I think this is a half-decent answer.
That's what I was thinking.
Right?
Massive paragraph. Nice.
So we could go with, aesthetically this is awful because it's one massive paragraph. Yeah, okay. Right? I do want to throw something in there. Notice that we did at least change the font, right? Italics. The italics was kind of a middle finger, sort of, if you will. Can anybody tell me what the italics is?
What the what?
What's in italics? Don't tell me the text. What's being written up there?
Rules.
Are you asking rhetorically?
He's
telling you to follow the.
Rewriting the question.
That's the question.
I'm establishing a thesis. Because someone who shall remain unnamed saw all the work I wrote down and was like, you're missing a thesis statement. I said unnamed.
I said this is solid. You didn't exactly say what your purpose was.
Doesn't exactly have a
And
good
then-
look either.
So, but this kind of process of dealing with that alphabetic text, okay, may seem ridiculous and painful and long, but it's that process that you should be going through and solving. When we go through to establish that conversion, it's not just feet and inches. Okay? When and where do you use those feet and inches? Because when you see that question, you're already starting to align those things because you know those unit systems. If you don't know the unit system, you're dead in the water. Right? That's why you need a process to establish why you place those units where you place them. That comes with practice following the method. Particularly, practice following the method with unit systems you already know so that you don't have an extra layer of crap to deal with on the next slide. Make sense? Okay. So, formula usage. If I was going to look at a wheel, we'll get very sick and tired of wheels and bikes. Okay? If I wanted to create a formula for the wheel shown, what would I use? Okay, spokes. Let's just say 32 spokes. Did really someone just say pi? You can F off. Spokes. We had wheel. Okay. We had one rim. Okay. We had one hub. Okay. Let's stop listing pieces. Okay. That's a lot of stuff to write out. Is there a shorthand I could come up with? Okay. Hub, rim, spoke, wheel, right?
Sure. 1H plus 1 R plus 32.
32 spokes. Does my formula show 32 spokes? No, so I want to include that 32. Where should I place that? in front of the spokes? Is that 32 rims or is that 32 spokes? Okay. Maybe after it. Is that 32 spokes or 32 wheels? Okay. We have to come upon a socially agreed upon norm on where to place that information so that we can constantly reference it and know where it's found. So in this case, if we use that chemistry system, we'd place it as a subscript immediately afterwards. Okay. Could we describe how to build said image? Well, we could say, I take one hub plus one rim plus 32 spokes plus one wheel
Equals one wheel with a bunch of parts.
equals that whole formula system. That whole formula system may be ridiculous. You might say, well, wouldn't we just call it a wheel? Okay, well, that becomes fun when dealing with all sorts of other nomenclature systems we don't have to address. Okay, what if I want to see the pieces that went into it? Okay. If we think about a name bike, what are the pieces in bike? Well, there's one B. No, you're an idiot, Mike. What are you talking about? Okay. Well, if I say bike, nothing about that name gives me anything about how it was built. I was waiting for someone to say that. Okay. You can shush. Okay. The name doesn't give me all of the components that go into it. When I look at the name bike, it doesn't tell me there's one seat post. Okay? Or it doesn't tell me there's two seat posts. Okay? So we invented a system in chemistry to address the basic pieces. That's our periodic table of elements. And we just change that sequencing. Yes, there are cases where these things become astronomically huge. The human body, if you try to write that as a chemical formula, or even the smallest molecule within the human body as a formula, it's awful. Okay? That's why we allowed biologists to come in and be like, it's DNA. Okay? To just remove a bunch of that information. Okay? So we have to decide what level we're at. In chemistry, we're looking very, very small systems. And so we invent a system that allows us to manipulate it. That system gives us the power to convert. If I'm going to build one wheel, I know that one wheel is going to require
More stuff.
32 spokes, one rim, and one hub. A chemical formula gives me that. If I look at the chemical formula for water, to make one water, I need two hydrogen atoms and one oxygen atom. The chemical formula gives me that information. I have to be able to needle that information out. What was that information for one molecule? That's fudge. Of water, and I know I'm missing letters, shush. One molecule of water, two atoms of hydrogen. What have I now created? A conversion factor. That conversion factor could now allow me to convert an infinite amount of molecules into the amount of hydrogen atoms. The chemical formula gives me that. That's chapter 8. Okay? The extra layer that goes with it comes up here. How many atoms of sodium are needed to make one molecule of sodium carbonate? What am I solving for?
Number.
Molecules of sodium carbonate. Is anybody else tired of writing molecules? Good. It is not accepted, widely accepted. I write MLC, not MOL, because unfortunately MOL means something else. MLC is our molecule. What molecule are we solving for? Sodium carbonate. Oh, I was right. Make one molecule of sodium carbonate. Yeah. Yeah, that sentence is bad.
Yeah,
Fixed. How many molecules of sodium are needed to react with 1 molecule of sodium carbonate? What am I solving for?
Sodium. Atoms of sodium.
Atoms of sodium. Sorry, the question was bad. What was I given?
1 molecule of sodium carbonate.
I'm going to say no to Nadia, who said 1 molecule of sodium carbonate, and I'm going to say yes to William, who said
Sodium, I don't remember.
molecule of sodium carbonate. Didn't they say the same thing? Nadia started with 1. That's a number. Don't start with the number. Start with the unit. The unit in this case is molecule of sodium carbonate. How many of those did I start with, Nadia? 1. Is molecules of sodium carbonate the same thing as atoms of sodium? No. So what do I need to do? I will do a conversion factor. In that conversion factor, what do I know needs to happen?
You need to remove carbonate.
Molecules to atoms. I'm going to convert molecules of water into atoms of molybdenum. Oh my goodness, Mike, stop being an idiot. If you don't specify that unit, guess what you do? Start converting to molybdenum. You're like, no, I won't. Look at your exam too. Right? It is very critical to fully address your unit. This is molecules, sodium carbonate, and this is atoms of sodium. Where do I find that relationship? Good look at the equation. The equation actually doesn't show sodium.
It's the moles of sodium carbonate. The second.
It's in the chemical formula.
So that's what I meant.
2 atoms of sodium are in 1 molecule of sodium carbonate. How many atoms of sodium do I need? 2. Can you do that math on your head? In your head. Yeah, and you're like, Mike, you're showing me a dumb process again because I can do this in my head. I'm showing you the initial steps so that you can write it down when I throw in 4 other conversions. You need those individual steps. What I'll leave you on, how much do 2 atoms of sodium weigh? Because I now know how to make a molecule of sodium carbonate. I need 2 atoms of sodium. I now need to go into the lab and I need to weigh out 2 atoms of sodium. Figure out what you can do with that.